Hi, welcome back, everybody, to another talk. Today, I will be discussing some safe-based reinforcement learning. I will be specifically talking about the following paper, which we call Saute RL, which is an ICML publication, and it does almost sure safe reinforcement learning by state augmentation. The beautiful thing about this method is that it's a plug and play, meaning that with minor changes to your environment, we are able to guarantee almost sure safety or safety with probability close to one. Now, the first thing is we need to understand why it's important to consider safe reinforcement learning. And we all know that in any real world application, was it robotics oriented or medically oriented or even aligning large language models with the humans, safety becomes a critical issue. So we're going to first understand how we deal with safety inside reinforcement learning, and then we're going to propose a method to tackle this, which is plug and play. So we're going to get started from the standard Markov decision process setup, right? So in reinforcement learning, right, as you saw in other talks, maybe in this channel, what we do is we start by defining a Markov decision process. So we call that here M standard, and that Markov decision process is made of a state space, so where the agent is, an action space, what actions the agent is allowed to take, a transition model, which tells me how the environment will go to the next state given I'm at the current state and apply the current action, and a cost function or a reward function, which tells me how well the agent is doing. Here, I just used cost to say it's minus the reward, but you could equivalently write this with the reward function. But cost is just like, okay, there's a cost, in the environment for taking a specific action. And of course, a discount factor, and that discount factor will allow me, right, to understand, to trade off, let's say, future rewards from current rewards or future costs from current costs. So this is the standard Markov decision process, right? We have a state space where I'm at, an action space, what am I allowed to take in terms of actions, a transition model, how the environment will behave, and a cost telling me how well I'm doing in that environment, and a discount factor. My goal in reinforcement learning, right, is to find a policy or an action selection rule, right, that will minimize the total cost that I incur in the environment. Probably you've seen this as maximize, and instead of cost, you had the reward, but really they're the same thing. You can just define the cost as negative the reward, and then you end up with a minimization problem instead of a maximization problem. So what we really want to do is in expectation or on average over the stochasticity of the policy and the stochasticity of the transitions in the environments, right? I want to find that policy, which is an action selection rule. So given a state X, it will map, to an action. I would like to be able to find that policy, which will minimize my total cost, which I call J task here. And that cost is simply the summation over the time of the costs that you have gotten for being in a state xt and applying an action at, and they are discounted with gamma to the power t, which is kind of the discount factor. So this is a standard reinforcement learning pipeline, right? So for example, if you were doing RLHF, then kind of your reward will be the model of the human preference pairs. And then you would be finding the policy by PPO, which is one way to solve, this problem. Okay. So this is the standard RL loop, right? Or the standard RL setup. we have an MDP, and then our goal is to find that policy which will minimize the total costs in the environment. Right. Now, when we want to talk about safe reinforcement learning, we rather deal with something called constrained MDPs and not just MDPs. So constrained MDPs are an extension of MDPs to support safety or constraint costs. So a constraint MDP is defined, right, as a standard MDP which had the state space, the action space, the transition model, the standard cost function, and the discount factor. But we're going to augment that with two additional components. Those are new components, which we are calling Z and gamma Z. So a constraint MDP, right, is the standard MDP, but we augment two new things to it. One is Z and the other is gamma Z. Z is a safety cost or a constraint cost. So Z is similar to the C cost, but it defines another cost function related to constraints or to safety. As is the case with the cost function, right, that it maps from state to actions into, in our case, positive real numbers, Z will also map the state and the action you are in, but more towards a safety cost, right? So the safety cost we have here, right, is the same as the cost, but now it's used to dictate our safety consideration. And similar to what we had in before as gamma, now we have gamma Z, which is a discount factor specific for that cost constraint. Why we have two gammas? Because, you know, if you are considering safety things, right, maybe you don't want to look a lot into the future, or maybe you would like to look a lot into the future, but there is no necessity to have the gamma Z equal to the gamma. You might have different considerations about that discount factor for your cost. Right. So we are able to go, right, from a standard MDP, which is kind of the MDP we described here, right, into a constrained MDP by taking the standard MDP and augmenting two additional things. One is this mathcal Z, which is the safety or constraint cost. And this constraint cost is like the standard cost, right? But it dictates our safety or constraint specifications. So what is the goal in a constrained MDP? So the goal in a constrained MDP is not only to find that policy, right, that will maximize or minimize my standard cost C, as you know we described here, because now we have these safety constraints, right, and we would like to meet those safety considerations. So instead of having an unconstrained problem, which is the standard MDP style, we will have a constraint problem where our goal is to minimize the standard cost. So this part is same as before. I want to find that policy, right, that will minimize my total cost. So if you look at this equation and you look at this equation, they're the same thing. So I still look for the good policy, but now I additionally have a set of constraint cost that I would like to meet. So I want to meet the constraint cost and also find the policy that minimizes my standard cost function. Now, how do we define this constraint cost? What we have done, right, is we have used a budget. So we defined a budget. We call that D, you know. We defined that budget D, And that budget is kind of how many times you're allowed to, make mistakes or violate that loss, right? And that we call the constraint budget. And then we define the constraint as the difference between that constraint budget, right, and all the costs that you have incurred so far. So this term here is all the mistakes that I have done so far, right, over my loop I'm running, right, over my interaction with the environment. And now D is my constraint budget. And what I really would like to do is I would like to find that policy pi, right, that minimizes my standard cost C, but also has a remaining budget of making mistakes. So I would like to have a bit of budget left from that policy in my violation of my safety cost. So now, when we talk about a constrained MDP, right, we would like to find a policy, standard policy, like before, but also it has to meet those budgeted, or it has to be feasible with respect to those budgeted constraints, whereby I would like to still have some budget left in my mistakes that I am doing. So if we ignore the expectation for a second, you can see that this equation is saying D is bigger than or equal to the sum of those costs, meaning that you still have some budget left, right? Budget of mistakes left. So that's the constraint budget left. Right, so now one way to describe safety inside reinforcement learning is you would define your Z, right? You would define a constraint budget, and then you would say, let me solve this constraint optimization problem, where I would like to minimize my costs, but also be safe with respect to those constraints, i.e. have a certain set of budget left. And now, as you see, because we said this Z function is the same as the C function, so now we also can just write it as the summation over Z xtat, like we wrote C of xtat. But now, instead of using the standard gamma, we have its own specific gamma, because we want to give you the flexibility, right, to have your own way of designing the safety cost. Good. So the standard way really of dealing with the constraint RL is kind of to do, this, and then to solve this form of a problem. So we go from the standard MDP to the constraint MDP, and then we tackle the problem that looks like this. Okay. Good. Now, how do we actually solve this problem? So we have a problem that looks like this, right? We want to find that policy that will minimize, the standard MDP cost, subject to these budgeted constraints on safety. But how do we actually solve this? Well, maybe the most common way to solve this, right? Because this is a standard, in a way, constraint optimization problem. You would write the Lagrangian of this problem by introducing Lagrange variables and then solve a min-max solution, right? And look for a min-max solution. So that's like a standard constrained RL kind of solution, right? It's like, or even constraint optimization. When you have a minimize a function subject to constraints, what we typically do is we write the Lagrangian of it, and then we turn that into a min-max problem. Now, if you're not familiar with this, if you look at the TRPO, it had these KL constraints, so it did something similar. If you look at PPO, it also had something very similar, right? Where we actually had this lambda times the constraint, but now we started scheduling the lambda, right? And playing with that lambda. But in general, right, if you want to solve a constraint optimization problem, then you're actually going to be looking into writing the Lagrangian of this by introducing those Lagrange variables lambda, and then you would be finding a min-max solution. So in other words, what we really would do is we would introduce those lambda Lagrange multipliers, and then we now can have an unconstrained problem because we just do minus lambda times, this term. And then instead of just solving the min, we also solve over the max. So we'll try to find in the max over lambda, the policy that will satisfy, that will minimize this total equation. Now, you can clearly see, I believe, right, that the optimal solution of this problem is when lambda, if lambda, so if we have, like, let's think about it intuitively, right? So if we have some budget left, right? So if this is positive, so if there's left budget, then maybe, set lambda equal to 0, so only focus on the cost term of the task. But if we are out of budget, be penalized a lot here and actually just focus more on meeting those constraints. So kind of an optimal solution, right, to the lambda problem here would be if you have some budget left, focus on the cost, and if not, just make sure you don't make mistakes. And that's how constraint MDPs are typically solved, right? So you would take this constraint problem, you would write it as a min-max problem, and then you would actually solve the corresponding problem, which will end up with an optimal solution for lambda, as I show you here. But what's the problem, with this min-max solution, which is maybe kind of the standard way of dealing with this? I mean, first of all, it's really hard to get it to work well because of many engineering and numerical instabilities. But there are also two fundamental questions that are actually not 100% tackled, right, by this problem. The first is that it is not clear if a Bellman-based solution would still exist if we have a constraint MDP in this form. Because it really depends, on those constraints. So it depends on what constraints you are really interested in. And there's not a clear constraint Bellman equation. How would that look like in the general case? Now, why is that important? Because remember, in order to be able to solve these types of reinforcement learning problems, we would need the Bellman equation to hold. Remember, so there was another slide that I described in this channel on how you derive the Bellman equation. But you would need those Bellman equations to actually work successfully. And in the general case, when the constraints are beyond an expectation, like a conditional value at risk or some other measure you are interested in, it's really not clear what the constraint Bellman equation will look like. But two, and maybe the more exciting question or more interesting question, maybe both are interesting, is what we would really like, if we think about it, is we would like our policy to actually be explicitly conditioned on some safety features, right? So when I take the action, when I take the action, what I want is I want my policy to actually take into account what sort of safety features, right, that I am considering. So I want to take this information somehow into account when I'm making a decision. I want to be able, if the safety feature, like if explicitly I am noticing, right, that, oh my God, I am gonna, exploit my budget. I want to take that into account explicitly as maybe an input to my policy, when I am making a decision. And this will lead to a more scalable solution because it's like a new state variable, right? Which I can plug in any standard RL method if I am able to do this, right? Okay. So now the question is, how would we do something like that? Because instead of going through this min-max problem, right, which is like, it's a very hard problem to solve, I would like to devise a new direction for this problem, which will be meeting the Bellman equations, So we are still Markovian and we are happy. And it's a part, the safety, yeah, becomes a part of the state variable, right? Which will allow me to take actions conditioned explicitly on the safety feature. Right. So how do we do that? Well, the easiest way to do this, right, is to augment the state space of the MDP. So let's think about this for a second. If I am able to change the state variable of my problem to take into account the safety consideration, right? If I am able to do that, say somehow I was able to do that, then my state space will explicitly include inside it the safety cost. And of course, I need to change the cost function to accommodate for that. But if I'm able to do this stuff, right, then I have a policy which is explicitly depending on the safety. And if I was smart by how I augment my state variable, then I would be able to write a Markovian transition again. So the question here is, what can I augment my state variable with and have a Markovian transition, have policies that explicitly take safety information into account? And if I have those two, then it's interesting because you need to just do slight changes in the environment code to be able to have a plug and play solution where anything could just plug and then you can solve the problem. Right. So our strategy to solve this problem, we are going to augment the state variable with some variable, with something, such that that thing takes safety into account, so takes the constraint somehow into account, and still allows us to have the Markovian transitions to make the Bellman equation hold. Okay. So our strategy is, so far, let's recap, right? What we've done is we defined a standard MDP, then we defined a constraint MDP, and we said to solve the constraint MDP, we could use the min-max solution, right, which is the standard constraint solution. But we said, right, that that this is not nicely taking safety into account, and also we do not explicitly know in the general case if the Bellman equations will hold. And then we said, okay, let's devise another form of solution to this problem by taking into account, right, a augmentation to my state variable. That augmentation, I wanted to take safety into consideration, so my policy, right, depends explicitly on safety features. And also I want to augment it in such a way, right, that I have Markovian transitions. Okay. Sounds good. So how do we do that? In order to understand this, let's go back and look at the evolution of the safety budget. So here, let's take the remaining budget constraint. So I call that omega at t-1. So what I am doing really is I am counting up to the current moment, right? I am counting all the mistakes I have done, right? And I am subtracting those from my safety budget D. So at time t-1, right, I can have D minus the mistakes I've done so far, right? And this is my remaining budget, the budget that is left for me, right? So really what this term is doing is like, okay, I will count, kind of all the mistakes I've done so far with respect to this cost, right? And my gamma Z. That's the total cost I accumulated in terms of constraint. And that's the total constraint cost or total safety cost. And then what I'm going to do is I'm going to take the D, right, which is my total budget, subtract from that, and that's kind of the remaining budget I have. So now what I'm going to do is I'm going to define my lambda t variable, right? So this is just a lambda t variable, okay? I'm going to define that as omega t minus 1 divided by gamma to the by gamma to the power t, gamma z to the power t. Okay, now why did I do this? I did all this stuff, right, to show you that I can get a Markovian evolution, right, of the safety budget. Because if I define the remaining safety budget like this, I can show you that lambda at time t plus 1, right, will depend on the lambda at time t. So this is kind of the safety state, yeah, at time t, minus the z, minus the cost at xtat divided by gamma z. So what you can actually show, right, is that lambda t plus 1, which is the evolution of the safety budget, is conditioned on information that is only t dependent, right? So here t plus 1, as you see, will depend only on t. It doesn't care about the history anymore. Whatever your safety budget is, or whatever your safety constraint is. Because this is nice, right? Because this is a Markovian dependence, then we can easily augment this in my state variable. Because now my state variable, remember, it has a Markovian transition going from t, xtat to xt plus 1, right? Now, not only I will have that variable xt, but I will also introduce this lambda t of safety inside my state space, and that itself will have a Markovian dependence. Okay, so let's recap what we've done here. We agreed that we want to augment our state variable by something that will explicitly take safety into account, and that thing that it takes into account should be Markovian, because if I want to augment my state variable, right, then I need to be able to deal with that in a Markovian fashion. So then we looked into the evolution of the safety budget. So we defined this variable, right, which is the left budget that we have, right, in safety. And we called that lambda. And we were able to show that lambda t plus 1 is a function of information that is only available at time t, lambda t and z of xt18. And because this has a nice Markovian dependence, now I can define a new state space, which is x cross lambda. So it's the standard state space, but also it has this lambda, which itself is, which we need, of course, to define its cost and its transitions. Okay, good. And now, because my state variable will be made of, x and lambda, so xt and lambda t, right? Because my state variable is made of those, now I need to be able to define a cost, right? Which is a function of the state and the action, but the state now is xt lambda t. So I need to define a cost state xt lambda t and the action a t. And that's what we are doing in this part in the step 2. So the way we define those costs, right, is we are going to define a cost c hat or c tilde. C tilde is now a function of the augmented state variable xt lambda t and the action at. And the way we define this is just the standard cost if you have some budget left. So if there's some budget left, focus on your task cost. And if there's no budget left, be punished a lot, get highly punished otherwise. And now we would actually be looking for a problem, for a solution to the following problem, where we would like to minimize with respect to the policy, right, the augmented cost, right? So now this becomes a nice constraint-free problem. Of course, there's an expectation here, which I forgot to put, but the whole idea is I would like now to minimize with respect to the policy pi, okay, the constraint-free problem, which has a cost c tilde, and it has a state variable xt and lambda t. So this in turn allowed me now to transform the constraint RL problem back into a Markovian looking problem, where I can do it by doing state augmentation, where I augment my state variable with this new variable lambda t, which has a Markovian evolution, so thumbs up. And I will change my cost to take into account this new state variable, so that if there is budget remaining, I will just focus on my task cost, normal standard MDP stuff. But if my budget is there's no budget remaining, then I will just focus on making sure, I don't violate I get highly punished, essentially. And then you would solve this problem. Now, please look at this problem, right? And now this problem is constraint-free, Markovian, meaning that you could use any RL algorithm you like to solve it. And you will guarantee that you will meet the safety constraints. So we actually proved in the paper that if you will solve this problem, you will get almost sure convergence or almost sure safety, meaning that if you're able to solve this problem, you're actually safe with respect to your constraints, or you are feasible with respect to your constraints. And now that is super cool, because now you can actually solve problems of safe RL using standard PPO, if you like, or using some model-based solver, or using whatever you like. Why we were able to achieve this? Because we did the trick, right? We were able to go from a constrained MDP into a constraint-free MDP by augmenting a Markovian state variable and changing the cost. And that takes us to what we define as safety augmented MDPs, or Saute MDPs. So remember, we had the standard MDP and we had the constraint MDP. So standard MDP, we've all seen it, XAP cost gamma. And the constraint MDP was X standard MDP, XAP cost gamma, and it added the Z, which is the safety or constraint cost, and gamma Z. Now, the Saute MDP is another form of an MDP. And what it does is that it will augment the state variable by this new variable lambda. It will change the transition in order to have the standard transition of X and the transition we defined of lambda before, i.e. this guy here. And then it will change the cost to just say, if my lambda, I have remaining budget, then focus on the task, otherwise be punished a lot. So before, we had like a plus infinity. I just here put a very high number during implementation, just to be computation friendly. And now we have a task that looks like this, which we would like to solve, right? Where now you can apply any standard reinforcement learning algorithm. So this augmentation allowed me to make a constraint-free problem that meets the Bellman equations, because it's Markovian, right? And more importantly, now the policy is explicitly conditioned on the state, right? But the state is X tilde, meaning that the policy is conditioned on the standard variable X and also on this safety budget lambda. And in reality, when I say, it's a plug and play to solve it, it is really plug and play. All you need to do is you need to do 3 very simple changes to your OpenAI gym to be able to execute, right, our method. So you need to design a safety step, right, which is just describing the, how the budget is changing of the constraints. You need to make sure that you reset correctly. And you need to make sure to change the cost so that you say, if the safety step is remaining budget, just focus on the standard reward, right? Or the standard cost in my math that I described. Otherwise, just get very highly punished. And it's really agnostic to what agent you use. So you can use model-free algorithm, because you see, those changes are to the environment itself and they're not to the agent. So now, instead of the environment returning just xt plus 1, right, which is what it used to do, it will return x tilde t plus 1. And instead of returning a cost, it will return this c tilde cost. And then you can use a model-free algorithm, a model-based algorithm, an actor-critic algorithm, an actor-only algorithm. It's really up to you. So of course we have implemented this, and it's open source as well, so feel free to use it. It's on this link, right? So it's under Hibo, under a Simmer or Saute approach. I will show you the exact file there. So in terms of experiments, right, we considered different types of tasks. So we considered a simple pendulum task and a cart pole task and like a robot arm task and some other tasks from, I think this was the safety gym. So here we wanted to have, like we have this sort of a unsafe region. Here we had these unsafe regions. And here we had this unsafe region where the robot needed to avoid it, if it's grasping this. And this car needed to arrive, to that destination, but it also needed to avoid the unsafe region. So those are some of the tasks we considered. But because I told you it's plug and play, I actually wanted to convince you that it is plug and play. So that's why we tried different algorithms. So we tried the PPO, right, as one of the algorithms to solve the problem. We tried TRPO, and we tried soft actor critic. Each one of those, we compared three things. We compared the vanilla one, right, without any safety consideration. We compared the Saute one, which is the method I described. We compared the Lagrangian one, remember, where you actually solve it by this Lagrange multipliers. And we compared to a constraint policy optimization, which is kind of another form of algorithm. We also consider safe algorithm or constraint satisfaction RL algorithm. We also considered things related to model-based reinforcement learning. So we took model-based policy optimization, and we took like probabilistic ensembles, which is kind of an MPC base. And we tried those with vanilla and with Saute. So as you see here, because we make the change to the environment and not to the agent, we're agnostic to which algorithm you like. So you could use PPO, TRPO, SAC, model-based, it's up to you. Whichever algorithm you think is more suited for your task, you could use it, and our method still guarantees that you will be safe almost surely. And here are some of those results. So here we look into A, B, C are different algorithms, right? So we have here PPO, SAC, TRPO. This is the cost pendulum problem. Right? And here we show you the different versions of the PPO, of the SAC, and of the TRPO. The green one is the safety cost, and the orange one, which you don't see, are the cost of the task itself. This line here is the line that we would like to meet in terms of safety. Now, if we look at the vanilla thing, we can see that it is getting for us a good performance, but it's really causing a lot of safety problems. If we look at our method, we can see that we're getting almost the same performance as the vanilla one, but at a much lower violation of the costs. If we look at the Lagrangian one, right, then what you can see is we do get a similar performance to the vanilla one in terms of the task, but in terms of the safety, we are actually sometimes violating the safety problem. Ours does not. If we look at soft actor critic applied to the same problem, right, then you can see that we see a very similar trend. So all of them, the Lagrangian, Saute, and vanilla, are able to get good task values, performance, but the costs or the safety costs are varying. So vanilla has a high safety cost. We are below the budget for sure. The Lagrangian is below the budget, but sometimes outside of the budget. This also can be seen in TRPO, where we also ran CPO. And now you can see that we get Saute would get below the budget for sure, and good value of the standard cost, this. While the other algorithms, while they get good value of the standard task cost, they actually can violate the budget as well. This is also shown in model-based settings, so MBPO or PETs, right? And then in all those, what you can see is that Saute is guaranteeing that we stay under, our safety budget or meet, be feasible with respect to that. But at the same time, has a good cost value with respect to the task itself. So that's why we call task and safety. So just to read this well, sorry, because maybe the representation is not great. The green one is the safety cost, and this orange, supposed to be orange one, is the task cost. So you always have green, orange, green, orange, green, orange. But because there's not a lot of variation in here, you don't see the orange. But all those, you should read them as green, orange for vanilla, i.e. safety task, green, orange for us, i.e. safety task, green, orange for Lagrangian, and so on. And then we also see a similar behavior in terms of the double pendulum. But what is really interesting to show is that always our safety is below, the constraint we have. However, the Lagrangian or the CPO can have extremely bad, unsafe behavior sometimes. So we also tried it on different tasks, right, as I described to you before. So this was for the reacher robot. So this was the robot that needs to reach somewhere and you have to avoid the thing. Again, we see that Saute is performing the best in terms of safety. And in terms of the task, they're all achieving similar solution. And we see the same thing with the car, right, where the car needs to reach somewhere but avoid this patch in the middle. However, here we can see sometimes we have a slight, going out from the safety boundary. However, the others are, going out a lot from the safety boundary. So here we did, things related to ablation study where we did not, for example, do this the state augmentation, or we did not do the cost shaping, and we see that the whole pipeline is actually better than that. Okay, this is the paper, and the code is available here, right? So if you go to the Hebo library, there's a file called Simmer. Under Simmer, you would find all these codes. Now, what we have described today is a method that does safe reinforcement learning, guarantees almost sure safety, is a plug and a play with respect to any of the algorithms you like. And that's what I love about this method. So it's not like we need to change every algorithm. You just need to change the environment a bit to take into account the augmentation of the state variable and the change of the cost with 3 very simple steps. And then you can actually guarantee almost sure safe. So thank you for listening. Please follow me on X at HBOAmmar or add me on LinkedIn. And if you find this useful, please do start our repo. So with that, I would like to end, and I would like to thank you all for listening. If you have any questions, please write them in the comments below it. If you find whatever we're doing is useful, please subscribe to the channel. Thanks a lot.